All right, dude, we are live. What's up, guys? This is Dem Keys, and today, hold on, give me a second. For some reason, it seems like my mic is really picking up the. Okay, I think it's much better now. Holy shit! Um, how much of that was picked up by the mic? I don't know, because like the funny thing is, even though the mic switch was off, it was still picking up audio signal if I set it loud enough and close enough. Which, I mean, I've noticed this before as well, but I never noticed it to this extent. Like I never noticed it being picked up to this extent. Either way, what's up, guys? This is Dem Keys, and today we are going to be taking a slight detour because I have a stats related thing that I found really interesting, and I was doing this off stream, and I figured, you know what, let's do it on stream. Now, let's take a scenario. Let's describe the scenario here. Okay, we have some trading data. The stream itself isn't trading related, but like this specific trading data, I found the pattern kind of interesting. So here we have, how do I say this? So okay, we have an asset. Okay, we have, let's say we have an asset that can be bought for a certain amount of dollars. And the price of that asset, it tends to fluctuate. So at different times, you might find different prices for it. And at different times, whenever you buy it, you're buying it at whatever the current price is, right? So let's say a trader has bought certain amounts of an asset at different times, at different prices. Let's say this is our data set that's showing the prices at which the trader bought these assets. Okay, the price was 3,830, then 3,850, 3,900, 950, 415. No, sorry, 4,015, 4,022, 4,025, and 4,040. So at each of these different price points, the trader bought a certain amount of the asset. How much did they buy? They bought, in some cases, $50 worth, in some cases, $100, one case, $100 worth, and in some cases, $30 worth. Okay, so depending on how much worth they wanted to buy, they got the appropriate amount. You get the appropriate amount um, by dividing the amount that you're willing to spend by the price. So then you're going to get the amount that you're going to get for that. Then you're going to get the, how do I say this? I feel like the word amount becomes kind of ambiguous. So let's say you're willing to pay $50. You divide 50 by whatever the current price is. So let's say 3,800, and whatever the result is, that is the amount that you would get of this asset for $50. Okay, that's fine. That's great, right? The trader bought certain amounts of this asset at different prices, at different points in time, at different prices. And they got certain amounts depending on how much they were willing to spend. So the first thing I wanted to find out is, let's say the trader decided to sell all of this, all of these assets that they're holding. Let's say they decided to sell it. What would be the minimum price that they would have to sell above in order to make a profit? And I think this is where dollar cost averaging can come in, because the idea with dollar cost averaging is you buy fixed amounts of an asset at fixed intervals. I mean, it doesn't necessarily have to be a fixed amount, but like yeah, let's say you buy a fixed amount at fixed intervals. So let's say you buy it for 3 months. In 3 months, let's say every week you're buying $100 worth of the asset, right? The idea there is that because of the price fluctuating, you could use dollar cost averaging and average out the price and sell when it's higher than a certain price and still make a profit. So it may not necessarily be a big profit. It could be a big profit, but you'd make some kind of profit. Okay, that's fine. Here, I was trying to calculate what the point is where you would be able to make a profit. Like, what is the price level that you would need to sell this at? And it turns out that, well, it's in the name, dollar cost averaging. So I don't know if dollar cost averaging is called dollar cost averaging because you're selling it higher than the average, but it turns out that the average price, the mean between all of these values, all of the prices that you bought at, that is your minimum price. So you have to sell higher than that average in order to make any kind of profit, and also, of course, get all of your money back. So okay, that's not what I was like. That's part of what I was looking into. Like this is the scenario that's set up, right? I wanted to explore this data set to see what interesting patterns I can find, because I find it kind of interesting that, for example, one of the many interesting things that I found in this is that you are able to spread out the risk. I don't even know how to explain this, but you're essentially spreading out the risk when you do this kind of dollar cost averaging. And depending on how much the price has steered away from, what it originally was, you could actually make a profit, right? But what I find interesting is this idea of kind of spreading the risk out across multiple instances. Another thing I wanted to look into is so I wanted to try and scale these values down using the standard scaler in scikit-learn. So okay, I visualized these points over here. Okay, so this is our price. This is, I believe, the amount. No, this is the total. This is the total, and then this is the amount. So let's visualize the amount as well. The total can be down here, and we can set up a thing for how do we want to visualize the amount. I mean, the amount can also be a bar graph. Doesn't have to be doesn't have to be a, what do you call it? A line graph. Okay, so x is x for x in range, length, amounts. And then our height is amounts. All right. Let's run this and see what this displays. All right, so this is what's being displayed here. These look similar, but they're not exactly similar. So what I wanna find out is so if you look at this price data set, if you look at the price array, it's in the thousands, right? Would it still maintain this same shape if I scaled it down? I think to a certain extent I kind of already know the answer, but I do want to test it out and see if we still get that same shape, even after scaling it down. And more importantly, I want to see if I scale all three of these things down, would they still have the same relationship to each other. I don't know how I'm going to test that out. I'm still not sure how I'm going to test that out. Hmm. You know what? Okay, I think this is something I should do off stream because there's a lot of thinking. I mean, to be fair, I do a lot of thinking and out of the other stuff as well. But yeah, I was going to use a standard scaler and try to scale this down and see if it still maintains that pattern. Because there's a lot of interesting stuff in like even the small data set, the small, it's, let's say we're looking at what, 7 8 trades. There's a lot of interesting stuff that I was able to find in that small data set alone. And I kind of wanted to experiment with it and explore it some more. I'm not sure if I should do that on stream though. I don't know. I don't know if I want to do that on stream or if I want to do more Hugging Face stuff, more Transformers stuff, because I do have that page open here. We could go through this instead. Dude, I started the stream the fully intending to play around with the trading data set, but I don't know. I'm kind of changing my mind now. What do I want to do? So okay, I was gonna explore. There's a bunch of exploration that I already did with this. I compared like prices and I found out what. So to be honest, I did a fair bit of the calculation off stream. I was gonna explore a bunch. I'm not exactly sure what I want to explore in this, other than that thing that I was mentioning. Um, that thing that I was mentioning where, sorry, zoned out. Other than that thing that I was mentioning where I want to try scaling down all the data and see if it still maintains the size. The size? No, the shape. So okay, we're gonna keep this aside. Um, I'm gonna retitle the stream to more HF transformers things. Right. I'm not gonna keep trying to decide if I want to do this or if I want to do transformers. I'm just going to jump to transformers because there was other stuff that I wanted to look into as well, stuff like this. But you know what? Let's for today. Let's give some time to transformers. And to be honest, I need to, speaking of giving time, I need to give time to that Kaggle 5-day Gen AI course as well. I don't want to take too long with it because, as in, I don't want to take too long to get to it because, dude, LLM related technology it's advancing fast. So I want to learn as much as I can quickly and kind of get up to speed with everything. Um, and there's quite a bit for me to look into there. Dude, we still need to get back to fucking PyTorch, dude. Doing like neural network stuff. Shit, I completely forgot about that. I was supposed to be exploring that as well. You know what? We're gonna explore that. We're gonna one of these days we're gonna get back to doing that. So right now I need to write this down somewhere that we need to finish learning transformers. We need to finish well, continue learning. So I maybe let's not say finish. We need to continue learning transformers. We need to continue learning about neural networks because I haven't even touched at least practically. I mean, theoretically, I have, but practically, I haven't touched convolutional neural networks and recurrent neural networks. And I feel like it's necessary for me to go into those topics as well, because from these three different types of architectures, you can make much more complex architectures. And if I'm going to be looking into the complex architectures eventually, like transformers, for example, I want to make sure I know some of the basic stuff. You know what? Hold on. So I'm gonna refresh this, and we're gonna try asking. Okay, so I'm learning deep learning, and I want to learn about the transformers architecture. So far, I only know about feed forward. I just wrote feed forward. Okay, feed forward. Near. Why am I writing it like this? So far, I only know about FCNNs, CNNs, and RNNs. No, actually, so far I only know about FCNNs. I'm yet to learn about CNNs and RNNs. Just to give it a bit of context and give it some idea of the level of wow the level of knowledge. There you go. The level of knowledge that I have in terms of neural networks, so it can give me hopefully information based on that level. To understand the transformers architecture, it's helpful to know how it differs from and improves upon earlier neural network models such as FCNNs, CNNs, and RNNs. Okay, so this is a whole other architecture of its own, which I'm guessing doesn't include either of the others. Or maybe it does. Maybe those the smaller parts that make up transformers include include FCNNs, CNNs, or RNNs. I guess I'll find out once I look into the parts. Okay, so key components of transformers: encoder decoder architecture, self attention mechanism, layers and sublayers. Okay, all right. So, encoder decoder architecture. Transformers use an encoder decoder structure similar to other sequence to sequence models. The encoder processes the input sequence and generates a contextualized representation, while the decoder generates the output sequence based on this representation. Okay, self attention mechanism. The core innovation of transformers is the use of self attention, which follows the model to weigh follows no which allows the model to weigh the importance of different input elements relative to each other. This is done through multi-head attention, where the input is processed in parallel across multiple attention heads, enabling the model to capture diverse relationships with the input sequence. I need to read that again. I didn't get it. The core innovation of transformers is the oh, the core innovation of transformers is the use of self-attention, which allows the model to weigh the importance of different input elements relative to each other. This is done through multi-head attention. This is done through multi-head attention, where the input is processed in parallel across multiple attention heads. I feel like I'm not paying attention as I'm reading this. My mind is somewhere else. Let's try that again. The core innovation of transformers is the use of self-attention, which allows the model to weigh the importance of different input elements relative to each other. Okay. This is done through multi-head attention, where the input is processed in parallel across multiple attention heads, enabling the model to capture diverse relationships within the input sequence. Okay, okay, now I kind of got it. Then we have layers and sublayers. Encoder layers. Each encoder layer consists of two sublayers, a self-attention mechanism and a feed-forward neural network. These layers process the input tokens together, capturing contextual information. All right. Then we have decoder layers. Each decoder layer has three sublayers. Self-attention, cross-attention to incorporate the encoder's output, and a feed-forward neural network. Give me a second. Okay. Where was I? All right. The self-attention in the decoder only attends to output generated so far. Wait. The self-attention in the decoder only attends to the output generated so far, while the cross-attention attends to the encoder's output. Okay. All right. How transformers work. Input embeddings. The input text is first converted into vectors using an embedding algorithm. These vectors are then passed through the encoder layers. Where the input text is first converted into vectors using an embedding algorithm. So there's a bunch to explore here. So we're going to repurpose this. We're going to repurpose this thing. All right, so we were supposed to be looking into the Transformers library, but we are looking into the Transformers architecture instead, which I'm perfectly fine with. All right, so what was I gonna ask? Okay, right. So I'm learning about um, the Transformers architecture. Sorry, zoned out. Okay. I haven't understood the concept of input embeddings. I know that a tokenizer takes input text and associates, no, breaks it down into smaller pieces and associates each piece with a number. But what's the deal with input embeddings? All right. So I had to give it some idea of what I know currently. So maybe it would be able to explain it in relation to what I currently know. All right. In the context of the transformer architecture, input embeddings are a crucial step in converting text data into a format that the model can process. Here's a detailed explanation of how input embeddings work. Tokenization. First, the input First, the input text is broken down into smaller pieces called tokens. These can be words, subwords, or even characters depending on the tokenizer used. Embedding layer. Each token is then converted into a numerical representation known as an embedding. These embeddings are dense numeric vectors that capture the semantic meaning of the tokens. Okay? Unlike simple numeric indices, embeddings provide. I'm curious about something else. So I'm going to repurpose this other tab just to clear my doubt real quick. Uh, I want to learn about the transformers. Actually, no. I am. Just so it doesn't try to teach me from scratch. Because this specific question, I'm asking like a specific doubt that I want cleared. Okay, I'm currently learning about the transformers architecture. So far, I only know about FCNN architecture. I am yet to learn about CNNs and RNNs. Should I learn those first and then learn transformers? Or would I be able to learn transformers even without knowledge of CNNs and RNNs? All right, let's see what the LLM says. Give me a second real quick. I need to do something. Okay, all right. Just a minute. We're gonna get to reading. All right, cool, great. Okay, so let's see what Llama said. To understand and learn about transformers, to understand and learn about transformer architectures, you do not necessarily need to have prior knowledge of CNNs or RNNs, although some background in deep learning concepts can be helpful. Here's a breakdown of the key components and how they work. Encoder decoder architecture. The transformer model is primarily composed of two main blocks, the encoder and the decoder. The encoder processes the input sequence and generates a contextualized representation, while the decoder uses the representation to generate the output sequence. The architecture is particularly useful for sequence to sequence tasks like translation. Okay, key concepts. All right, so we're gonna look at the other thing, which is hopefully gonna explain all of this stuff. Actually, this doesn't mention positional something, positional encoding. Okay, so maybe I should come back to this as well. So far it has mentioned feed-forward neural network, which is fine because I know about feed-forward neural networks. Uh, right, learning transformers without prior knowledge of CNNs and RNNs. While understanding CNNs and RNNs can provide a broader context and help in appreciating the innovations of the transformer architecture, it is not a prerequisite. The transformer's unique use of self-attention and its encoder-decoder structure can be learned independently. That is good to know. That is great to know, actually. Starting with the basics of deep learning and then diving into the specifics of um, the transformer architecture should be sufficient for a comprehensive understanding. That is very helpful. Okay, cool. Give me a second. Okay, so I'm gonna need like 2 minutes, because I have some stuff to do that I'm gonna do. I also just remembered that there's this ad timer, which is gonna be, well, there's an ad gonna be playing in like 50 seconds from now. So here's what I'm gonna do. I'm gonna start the ad break now, and then I'll see you guys in 30 seconds. Where's the button? I think it's this one. Yeah, I'll see you guys in 30 seconds. Okay, I just realized that despite me clicking the run ad button, it did not register the click because my mouse is old. So this is awkward. There's going to be an ad playing in maybe 10, 15 seconds now. Okay, so that was, I think, 191. I think that's about it. Yep, that's about it. And there's the ad break. So yeah, I'll see you guys in 30 seconds. I'll take a hydration break in the meantime. Okay, welcome back. You know what I'm realizing? I need to learn to not talk loud, um, or rather, I need to learn to just speak with a relaxed voice, as opposed to, slightly louder or slightly high pitched or whatever. Because in most cases, my voice is usually not that great at that, or my vocal cords are usually not able to do that for very long. Um, there was gonna be a but also. I don't remember what the but also was, but yeah. Generally, I what am I trying to say? I need to learn. I need to remember, not learn. I know how to do it. I need to remember to just keep my voice kind of relaxed because I've noticed, and I noticed this a lot yesterday, which I was confused about why it was happening, but it's just the way my voice is. It doesn't do very well when I'm trying to speak loud. So that's why I have to like even turn my mic and all that up. There's a bunch of like gain filters on the mic, and it works out well because my vocal cords are a lot more relaxed when I'm speaking this way. I'm able to speak for longer, and to be honest, I kind of like speaking this way as opposed to speaking a little louder. I know I'm saying louder, and I don't know if it even sounds that loud on stream or not, but like I can tell the difference. I can definitely tell the difference when the voice is kind of like struggling to come out. But anyways, okay, let's carry on reading this thing. So we went through the tokenization thing. Then we have embedding layer. So each each token is then converted into a numerical representation. Now, okay, so I need to keep in mind, or I need to, well, figure out, not keep in mind. I need to look into whether the numerical representation is different from what happens during tokenization, because the token itself is also a number, right? It's represented as a number. The input is broken down into smaller pieces. Wait, hold on. No, I think. Wait, I need to hold on. So, um, when we pass input through a tokenizer, it breaks. What am I trying to ask? Yeah, it breaks the input text into smaller pieces called tokens. Are the tokens uh, represented as numbers? If so, how does this numerical representation differ from that in the embedding layer, or that in input embedding? Oh, okay. There's quite a bit of information here. Okay, when you pass input text through a tokenizer, it indeed breaks the text into smaller pieces called tokens. Here's how these tokens are represented and how this representation differs from input embeddings. Tokenization and integer representation. During the tokenization process, the text is split into tokens, which can be words, subwords, or characters depending on the tokenization strategy. Each token is then mapped to a unique integer. Uh, wait, each token is then mapped to a unique integer ID based on the tokenizer's predefined vocabulary. This process is often referred to as encoding. Oh, that's interesting. I didn't know that. Okay. For example, the text, "Don't you love Transformers?" might be tokenized into "Don't you love Transformers?" and the question mark. And each of these tokens would be assigned a specific integer from the tokenizer's vocabulary. All right. Dude, we should try making a tokenizer. Or, well, a very basic tokenizer. I don't know. I think that would be interesting. I think that would teach us a lot about, well, tokenization. Where was I? Yeah, okay. The tokenizer uses a lookup table. The tokenizer uses a lookup table to convert each token into its corresponding integer ID. This integer ID is what the model actually processes rather than the text itself. For instance, if the token if the token "don't" is mapped to the integer ID 123, then the model uses this ID to retrieve the corresponding vector representation from an embedding table. All right. Input embeddings. Input embeddings are vector representations of these tokens. Input embeddings are vector representations of these tokens. Okay. Once the tokens are converted into their integer IDs, these IDs are used to look up the corresponding vector representation in an embedding table. The embedding table is a matrix where each row corresponds to a unique token ID, When a token ID is used to index this table, it retrieves a vector embedding that represents the token in a way that the model can process. These vectors are trainable parameters that are adjusted during the model's training process to capture the semantic relationships between tokens. All right. Key differences. So I'm kind of understanding this. I still don't fully understand it. I need to read a lot more on this, but yeah, it seems like the integer representation that you get from okay, this is what I'm getting. You pass input to a tokenizer. The tokenizer gives you a numerical representation, and then that numerical representation um, can be indexed in an input in an embedding table to get a vector representation. I'm not sure what the vector representation contains, but apparently that vector representation is the input embedding. Uh, oh yeah, okay. I think that's yeah. If I carry on reading, I just noticed what the next thing was saying there. But yeah, okay. Key differences. Let's read the key differences. So integer representation. The integer IDs are simply indices into the embedding table and do not carry any semantic meaning of their own. Oh, that's interesting. They are a compact way to represent tokens. I didn't know that. Okay, all right. Input embeddings. Dude, I need to visualize this stuff. I need to visualize this stuff to understand it. Though I'd imagine trying to visualize an input embedding table or just an embedding table is going to be kind of a nightmare because, like, it's going to be massive, right? Though, I mean, I want to see at least a small chunk of it to get an idea, just so my own brain can start to form patterns about how things are connected. Okay. Did I read the input embeddings thing? I don't think so. Okay, input embeddings. The input embeddings, on the other hand, are the vector representations of these tokens. These vectors capture the semantic meaning and context of the tokens, allowing the model to understand and process the input text effectively. Okay, so far, what I just read, I don't understand. I mean, I understand it on like a very high level, but I want to understand how this works in practice. And I feel like in order to do that, I need to implement this myself. Um, so we're gonna have to get into that at some point. In summary, the tokens are first represented as integer IDs through the tokenization process, and these IDs are then used to retrieve the corresponding vector representations, which are input embeddings, from an embedding table, which are the actual inputs to the model. So the input embeddings are what are inputted into the model because that's the vector representation. All right. Okay. Um, I was gonna ask a question. Oh, yeah. What exactly does the vector representation contain? In the context of NLP, okay, let this. Okay, in the context of NLP, the vector representation of text, whether it be words, phrases, or entire documents, contains several key pieces of information that enable machine learning models to understand and process the text effectively. Here's a detailed breakdown of what these vector representations typically contain. Semantic meaning. Vector representations such as those generated by so and so, so and so, so and so capture the semantic meaning of capture the semantic meaning of the words or text segments. This means that words with similar meanings or contexts are represented by vectors that are close to each other in the higher dimensional vector space. All right. For example, the vectors for king and queen would be closer to each other than the vector for car because they share similar semantic properties. Contextual information. These vector representations are often contextually aware, meaning they take into account the word's surroundings in the text. For instance, word to vex, skip gram, and continuous bag of words models learn to predict context words. Wait, hold on. What? Learn to predict the context words given a target word or vice versa, which helps in capturing the contextual relationships between words. Okay. Syntactic and semantic regularities. The vectors can also capture syntactic and semantic regularities. For example, the famous example from word to vec illustrates that the vector representation can capture algebraic relationships such as king minus man plus woman equals queen. Uh, I don't get what that means, but okay. Which shows that the vector can encode both syntactic and semantic properties of the words. Dimensionality and density. Vector representations are typically high dimensional, meaning they have many features, often in the range of 100 to 300 dimensions. These vectors can be dense or sparse depending on the method used. For example, word to vec and glove produce dense vectors, while methods like bag of words and TF-IDF can produce sparse vectors. Document and chunk level representations. Beyond word level representations, techniques like doc to vec and chunk embeddings generate generate vector representations for larger units of text, such as documents, sentences, or chunks, phrases, or clauses. Okay. These representations capture the overall meaning and context of the larger text segments, which is okay. I find this part interesting. It being able to capture context and meaning. I need to explore that more. How exactly it's able to capture the context and meaning. And I found the other thing interesting as well, where it mentioned, where was it? I think it was under contextual information. No, semantic meaning. I'd learned about this through somebody else's post on LLMs, where they had mentioned this thing of they gave a two-dimensional example because that's the easiest thing to visualize. You can't visualize higher dimensional. You can't really visualize like 100 200 dimensions, right? So they gave a two-dimensional example of words being close to each other and being assigned like different values, and that is how it's able to capture meaning from something. So I wanna explore that more at some point as well. These representations capture the overall meaning and context of the larger text segments, which is useful for tasks like document classification, sentiment analysis, and named entity recognition. Training and optimization. The process of generating these vector representations involves training neural networks or other machine learning models on large corpora of text. The goal is to optimize the vector representation so that they capture the most relevant and meaningful aspects of the data, of the text data. This is often done using stochastic gradient descent and backpropagation. Okay. In summary, the vector representation in NLP contains the semantic meaning, contextual information, and syntactic and semantic regularities of the text, making it possible for machine learning models to understand and process natural language effectively. Okay, all right. Coming back here, we were looking into embedding layer, right? Okay, so each token is converted into a numerical representation known as an embedding. These embeddings are dense numeric vectors. Wait, each token is then converted. So the token is already an ID, right? It's saying here that the token is being converted into a numerical representation known as an embedding. These embeddings are dense numeric vectors that capture the semantic meaning of the tokens. Unlike simple numeric indices, embeddings provide a way to represent words in a continuous vector space, allowing the model to understand the relationships and nuances between different words. Example, to illustrate, consider the token 8. Instead of just assigning a numeric index to 8, an embedding layer would convert 8 into a vector. Example, a 512 dimensional vector that captures its semantic meaning. This vector would be close to other words representing words with similar meanings, such as eaten or consumed. Positional encoding. Since transformers do not have a recurrence mechanism like recurrent neural networks, they need a way to understand the position of each token in the sequence. Give me a second. Okay, where was I? Uh, yeah. Okay, they need a way to understand the position of each token in the sequence. To address this, positional encodings can positional encodings are added to the input embeddings. These encodings use sine and cosine functions to create vectors that represent the position of each token in the sequence. Interesting. Okay, this ensures that the model can understand the context and order of the tokens. I need to look into this more. Dude, there's a lot to explore here. There's quite a bit to explore here. If I break this down into like different, like smaller components, um, I think that'll be better for me because then I'll be able to keep track of all the stuff that I need to look into. Okay, process summary. Here's a step-by-step summary of how input embeddings are generated. Tokenization. The input text is broken down into tokens. So at this point, they're IDs. Just going to assume that they're IDs. Embedding. Each token is converted into a numerical vector embedding that captures its semantic meaning. So that's a vector. Okay. Positional encoding. Positional encodings are added to the embeddings to provide information about the position of each token in the sequence. Okay, I'm a little lost on that part in terms of like, because I'm trying to visualize all of this that I'm reading. I'm kind of lost there, but okay, let's carry on. Input to encoder. The resulting embeddings with positional information are fed into the encoder part of the transformer model. Okay, explain what happens in the encoder. Okay, in the transformer architecture, the encoder is a crucial component responsible for processing and encoding the input sequence into a continuous representation that the decoder can use to generate the output. Here's a detailed breakdown of what happens in the encoder. We do tokenization where Okay, so that's ID. Then we have the embedding layer. Each token is then converted into a numerical vector representation known as an embedding using an embedding layer. This layer maps each token this layer maps each token to a fixed length vector that captures its semantic meaning. Okay, all right. These embeddings are often initialized with pre-trained word embeddings, such as, wait, what? These embeddings are often initialized with pre-trained word embeddings, such as word2vec or glove. All right. Okay, then positional encoding. To provide information about the position of each token in the sequence, positional encodings are added to the embeddings. This is necessary because the transformer model does not have a recurrence mechanism like RNNs and needs a way to understand the order of tokens. The positional encodings use sine and cosine functions to create vectors that represent the position of each token. All right, then we have encoder layers. Stack of encoder layers. The encoder consists of multiple identical layers, typically 6 in the original transformer model. Each layer has two main subcomponents: a self-attention mechanism and feed-forward neural network. Okay, so the self-attention mechanism layer allows the model to weigh the importance of different tokens in the input sequence relative to each other. It computes attention scores that indicate how much each token should focus on other token how much each token should focus on other tokens in the sequence. This is done using multi-head attention, which allows the model to jointly attend to information from different representation subspaces at different positions. I need to read that again. Hold on. It computes attention scores that indicate how much each token should focus on other tokens in the sequence. All right. This is done using a multi-head attention, which allows the model to jointly attend to information from different representation subspaces at different positions. Okay. Feed-forward neural network. After the self-attention mechanism, the output is passed through a feed-forward neural network. This neural network consists of two linear layers with a ReLU activation function between them. The feed-forward neural network further processes the output from the self-attention layer and helps in capturing more complex patterns in the data. Layer normalization and residual connections. Layer normalization and residual connections. Each sublayer, self-attention and feed-forward neural network, is followed by layer normalization and residual connections. Layer normalization normalizes the activations of each layer, and residual connections help in mitigating the vanishing gradient problem by allowing the gradients to flow more easily through the network. Output of the encoder. Contextualized representation. After passing through all the encoder layers, the final output is a sequence of contextualized representations or embeddings for each token in the input sequence. The output is a sequence of contextualized representations or embeddings for each token in the input sequence. These representations capture the context and relationships between different tokens in the input space, in the input sequence. Okay, the output is then passed to the decoder to generate the output sequence. Uh, okay, what happens in the decoder? All right, in the transformer architecture, the decoder is responsible for generating the output sequence, typically in tasks such as machine translation, text generation, and other sequential output tasks. Okay, here's a detailed breakdown of what happens in the decoder. Output embeddings and positional encoding. The decoder starts by processing an input token, often. Okay, hold on. I'm gonna pause here. So this kind of seems like the opposite of what happened in the encoder, and in that order as well, I think. No, maybe not in that order. No, no, no. Okay, okay, no, no, no. I'm mistaken. Maybe it's not in that order, and there's also different stuff happening. It's not nearly the same. Okay, also, something that I need to something that I'm realizing is that there's a lot of different moving parts to the transformer architecture. I'm going to have to study this bit by bit. Before getting into the transformer architecture, I need to learn about these individual components and how I can use other tools to generate these components, or how I can use other tools to use these components. Kind of like how when I was trying to learn how to create feed forward neural networks, I was trying to break it down into individual components, like the linear layer separately and the ReLU function separately. I was trying to use each of them individually to see what they do and how they react, so I could understand their calculations. Okay. Okay. So transformers is also used in computer vision. That's interesting. You know what? I wanna ask this question. So transformers is also or transformer architecture is also used in. I'm intentionally asking this question in a very noobish way, because the transformers architecture and convolutional neural networks, these are like two different architectures that work differently, and they can help solve different problems. But I different problems. But I want to try and ask the question here so I can get like some information. So the transformer architecture is also used in computer vision. Interesting. I thought CNNs were more useful for CV. I'm purposely asking this question so I can get sort of a comparison between the two architectures, because yes, when you're learning about convolutional neural networks, images are kind of used as examples. Indeed, transformer architectures originally developed for NLP have been adapted and are now widely used for computer vision tasks, often referred to as vision transformers. Okay. Key differences from CNNs. Processing input. processing images as sequences. Unlike CNNs, which process images directly at the pixel level and exploit spatial hierarchies and local patterns, visual transformers treat images as sequences or patches. These patches are flattened and then linearly embedded into 1D vectors, which are then used as input tokens for the transformer architecture. Self-attention mechanism. Vision transformers leverage the self-attention mechanism to capture global contextual information and long-range dependencies within the image. This allows the model to focus on the most critical regions of the image, um, similar to how attention works in NLP tasks. Architecture of vision transformers. Image patching, transformer encoder, training and fine-tuning. Okay, advantages and applications. Efficiency and accuracy. Vision transformers have shown to be more vision transformers have shown to be computationally efficient and achieve high accuracy in various computer vision tasks. They can outperform traditional CNNs in terms of computational efficiency and accuracy in some cases. Applications. Vision transformers are applied in a wide range of tasks, including image classification, object detection, image segmentation, action recognition, generative modeling, and multimodal tasks. They are particularly useful, they're particularly effective in tasks that require capturing global context and long-range dependencies. All right, comparison with CNNs. Complementary capabilities. While CNNs excel in tasks where spatial hierarchies and local patterns are crucial, especially with limited data, vision transformers offer a different perspective by capturing global contextual information. I feel like that can be uh sorry, got distracted for a bit. So what was I saying? I was saying, yeah, I feel like considering considering the different um how do I even say this? Considering the different types of information or the different types of patterns that are captured from an image by both of these architectures, because both of these architectures, they seem to capture different, what's the word I'm looking for? What do they capture? They capture different, they capture information in different ways. I'll put it that way. They capture information in different ways, be it patterns, or be it context, or be it whatever. They capture the information in different ways, and they're getting different types of information because of the types of architectures these are. They capture different types of information from that same image, meaning they can each have their own use cases. I don't know which one is used more widely, but because given this difference, they both could serve their own separate purposes. Right. This makes vision transformers a valuable addition to the computer vision toolbox, rather than a replacement for CNNs. True, true. Scalability and flexibility. Vision transformers can handle images of varying resolutions and are effective in transfer learning, allowing them to pre-train on large datasets and fine-tune for specific tasks with limited labeled data. You know what? I have a question that I'm going to ask it. Actually, yeah, maybe let's ask it here. I'm learning about the transformers architecture. I'm wondering how much of it is used in stable diffusion models? Because I feel like diffusion was its own thing. Like that's a separate thing that I need to learn. I don't know if it's somehow based on transformers because like I haven't had the chance to read up on it. I don't know if diffusion is like its own separate technique. In the context of stable diffusion models, the transformer architecture has been increasingly integrated, particularly in the more recent versions. Here's a detailed look at how transformers are used in these models. The latest version of stable diffusion marks a significant departure from the earlier architecture by incorporating a transformer-based approach. Rectified flow transformer. SD3 uses a rectified flow transformer instead of the traditional UNet backbone. This architecture implements the rectified flow method with a transformer, which enhances the model's performance and efficiency. Multimodal diffusion transformer. The SD3 architecture is named multimodal diffusion transformer because it mixes text and image encodings within its operations. This involves tracks. This involves three tracks for original text encoding, transform text encoding, and image encoding in latent space. The transform text encodings and image encoding are combined during each transformer block, allowing for a more integrated processing of text and image information. Diffusion transformer. The concept of diffusion transformer has been applied to improve the performance of diffusion models. Here's how it relates to stable diffusion. Replacement of UNet. In diffusion transformer models, the traditional UNet convolutional neural network is replaced with a transformer. Wait, hold up. This change has showed significant improvements in performance, especially in terms of generating more realistic images. The transformer processes the noisy image embeddings broken down into a series of similar into a series of tokens similar to how text is processed in NLP tasks. Tokenization and processing. The noisy image embeddings are tokenized and processed within the transformer blocks. This involves learning to estimate the noise to be removed from the image, which is a critical step in the diffusion process. Wait, so if transformer architecture was recently integrated within uh, SD models, what did they use previously? Okay, before the integration of transformer architecture in the latest version of stable diffusion models, the earlier versions relied on a different architectural step. Here's a breakdown of what was used previously: latent diffusion models and UNet. In the versions of stable diffusion prior to SD 3.0, the models were based on latent diffusion models. Uh, oh, I thought there was going to be an and. Okay, they were based on latent diffusion models. Here are the key components: variational autoencoder. The VAE, the VAE was used. Let's just say VAE. The VAE was used to compress images from pixel space into a smaller dimensional latent space. Oh, I think I remember reading about this, or actually hearing about this when I was watching that, or when I was listening to that. Well, watching when I was watching that lecture. on convolutional neural networks, or maybe it was on recurrent neural networks, or maybe it was in so there was a transformers segment in there, and I think somewhere in between convolutional neural networks and transformers, they were talking about latent space and variational autoencoders. The VAE was used to compress images from pixel space into a smaller dimensional latent space, capturing the fundamental semantic meaning of the images. Capturing the fundamental semantic meaning of the images. That's interesting. Okay, UNet. The UNet composed of a ResNet backbone was employed for the denoising process. It operated on the latent space representations, iteratively removing Gaussian noise to generate the final image. This process was part of the forward and reverse diffusion steps. Diffusion process. The diffusion process involved iteratively applying Gaussian noise to the compressed latent representations and then using the UNet to denoise these representations, effectively reversing the noise application process to generate the final image. Text encoding. Text prompts were encoded using separate text encoders, but these encodings did not interact directly with the image encodings within the same transformer blocks as in wait, hold on. Did not interact directly with the image encodings within the same transformer blocks as in the newer versions. Instead, the text encodings influence the image generation process through conditioning the the diffusion model. Sorry, my reading, it goes to shit sometimes when I'm trying to read and understand at the same time. Okay, in summary, the previous versions of stable diffusion models used a combination of variational autoencoders. Isn't that what it is? Variational? Yeah. Variational autoencoder for compression, UNets for denoising, and separate text encoders for conditioning without the integrated transformer architecture that is now present in Stable Diffusion 3.0. All right. Okay, great. Awesome. Okay, cool. So I'm excited to no, you know what? I have another question. Let's give some context. I'm learning about the transformers architecture. Is there I'm pretty sure PyTorch, like at some point they might have introduced tools to allow you to build transformer architectures, like, with your own pieces, but I still want to ask the question so I can get all of the information. Okay, I'm learning about the transformers architecture. Is there a way to create my own custom transformers or transformer architecture? I keep saying transformers architecture. I don't know if the singular or the plural one is more accurate, but I'm not sure. Is there a way to create my own custom transformer architecture using PyTorch? Okay, so there's quite a few moving parts in here. There's a lot of moving parts in here. Um, I'm sure there must be documentation on. Yeah, you know what? Let's do that. I'm sure If they don't have like official documentation, then there's probably going to be documentation, not documentation, but like a tutorial written by a community member, or maybe somebody in the PyTorch team has made an official tutorial. Let's check. Hold on. PyTorch transformers. Okay, there's this. There's something on Hugging Face transformers as well. Let's look up building models. Okay, build transformer tutorial. Okay, all right. We are gonna open this and open this. Awesome. Oh, okay. They have a class for it, straight up. Okay, so a transformer model. User is able to modify the attributes as needed. The architecture is based on the paper. Attention is all you need. Um, okay. All right. Okay. Okay. All right. Cool. So we're able to define a bunch of these. Uh, a full example to apply transformer module for the word language model is available here. Wait, this is an entire class. What if I wanted to implement this class from scratch? Well, I don't want to. Well, not exactly from scratch. Rather, actually, I don't know what I'm trying to. I think that's the important thing I need to understand here is that I don't yet know what it is that I'm trying to do that's different from what this is currently allowing me to do. So I think we can just stick with what it's currently allowing us to do, and then I'll look for something else later if there's a need for it. PyTorch implementation of popular NLP transformers. What is this? What am I looking at here? PyTorch transformers, formerly known as PyTorch pre-trained BERT, is a library of the state-of-the-art pre-trained models for natural language processing. The library currently contains PyTorch implementations, pre-trained model weights, usage scripts, and conversion utilities. I should keep this in mind for later. Yeah, I should keep this in mind. Okay, all right. Okay, is transformers maybe transfer? Oh, there it is. Okay, right. Let's see what pops up here. Wait, only two. Okay, that's fine. That's fine. When the time comes, when I do look at, actually, I'm looking into it now. Why? Hold on. Why are there no tutorials on this? Or maybe I just need to look for it. There's documentation, then there's vision transformers, or vision transformer. Tutorials, a better transformer for fast transformer inference. Uh, yeah, I'm not Sure. The vision transformer model is based on the an image is worth 16 by 16 words, transformers for image recognition at scale paper. Okay, so I think I'll get to vision transformer after this. Dude, I need to write down. Okay, I need to make a list. Hold on. I need to make a list of all of the stuff that I need to look into. Okay, give the notebook a second. It's taking some time. All right, cool. Okay, so let's create a list. So, um, first transformers. I'm gonna change the order later on. Transformer architecture. Okay. Under this, we can have all of the smaller stuff. So we look into tokenizer. Actually, I should tokenizer is a separate thing. I should look into tokenizers separately. All right. Within transformer, we have input embeddings or input embedding. Oh, also let's look into VAEs. Might as well add CNNs and RNNs because I'd been meaning to look into those as well. Uh, what else? There was a thing about latent space. Let me just write that down. Something about latent space. All right, input embedding. Um, then encoder, decoder, attention. What else? What else is part of? For now, this is what I've got. So this is our list. Actually, play around with feed-forward neural networks more. Oh, also NLP in general. Okay, now let me try asking this thing a question. Let me try asking Llama. I shouldn't call it this thing. That doesn't sound good to say. Let me try asking, anyways. Let me try asking Llama a question. So, I'm learning. What was I about to ask? What exactly was my question? Let me go back to the text. NLP, yeah. So, I'm learning. No, I want to learn NLP. I don't know the basics. I have access to Python and various um, NLP and machine learning, or NLP and I guess let's add in deep learning libraries. All right, so there's a good bit of information here. Because okay, I do wanna look into NLP itself, but like I need to figure out the threshold. I need to figure out the point where I need to stop trying to go lower. How do I explain this? I like to go down to the low level to understand things, but with such complex things, you kind of need to find the point where you need to stop. Um, the point where going any further is not necessarily going to benefit you all that much. Let me put it that way. I need to find that point where going any deeper to try and implement things from scratch is not going to benefit me all that much, and then I need to like build my way up from there. And that is somewhere within NLP. I'm pretty sure there are things in NLP that I'm not going to need to do from scratch, and certain things that, um, well, they would also be really hard to do from scratch completely. I mean, possible to do, definitely, but like really hard to do from scratch completely. And I shouldn't need to do those things. I'm pretty sure I won't need to do those things because there are already tools available. So I need to sort of explore all of my options. To get started with NLP using Python and various NLP and deep learning libraries, here's, oh shit, I missed the ad timer. Or so there'll be an ad playing now in some time. Oh, there's the ad. All right, so I guess I'll take a hydration break in the meantime. All right, welcome back. Where was I? Okay, so Python and machine learning fundamentals. Before diving into NLP, ensure you have a solid foundation in Python programming and machine learning basics. All right, okay. Python programming, machine learning. Okay, cool, cool. Introduction to NLP and essential concepts. Learn what NLP is, its applications, and the fundamental concepts. Introduction to NLP. Understand the scope and applications of NLP, such as sentiment analysis, text classification, machine translation, and question answering. Linguistic linguistic concepts. Learn about tokenization, stemming, lemmatization, part of speech tagging, named entity recognition, and dependency parsing. Oh, good. Okay, they're explaining a bunch of these things. Wait, where was I? Tokenization. Tokenization involves breaking down text into smaller units called tokens. This can be word level, subword level, or character level tokenization. Stop word removal. Remove common words like the, is, and that do not add significant meaning to the text. Stemming and lemmatization. Reduce words to their base or root form. Stemming uses heuristic rules, while lemmatization is more complex and accurate but conceptually expensive. All right. Text processing. Text pre-processing. Just a second. Okay, yeah. Sorry. Um, text pre-processing. Text pre-processing is crucial for preparing your data for NLP tasks. Case normalization. Convert all text to a single case, lowercase to ensure consistency, removing punctuations and numbers. Clean the text by removing unnecessary characters, handling stop words, remove so and so. All right, traditional NLP techniques. Understand traditional NLP techniques before moving to deep learning. All right, so I don't think I need to, or okay, I could be wrong here, but I'm just I'm just gonna pick a certain point and be like, yeah, I don't think I need to go any deeper than that. Um, I think it's this part, text pre-processing. I don't think I should even be looking into text pre-processing, or maybe I could try. Let me. Okay, so a bunch of the things that are being done by these, or a bunch of the tasks that are being described here, I need to see to what extent these are already possible using currently existing models. And I mean, the answer to that is yeah, it's very much possible. I know that a bunch of different models exist. A ton of like free models exist that do this, but I want to try and go to a lower level up to a certain point. Right. So understand traditional NLP techniques before moving to deep learning. Bag of words and TF-IDF. This converts text data into numerical form using one of those two representations. Okay. So up here, up to this point, tokenization, I think it should come later on, right? After you remove the stop word removal and after you, I'm still not sure what you do in this, reducing words to their base or root form. You know what? I'm gonna ask another question. But okay, there's different NLP techniques. Ngrams capture the context. I think I could start by learning the NLP techniques as opposed to learning NLP from scratch completely, because I don't think I need to at this point. Hidden Markov models. The hidden Markov models and latent uh, di- ho- what Dirichlet allocation or Dirichlet. I'm not sure what the C how the CH is meant to be pronounced. Let's just say LDA. Hidden Markov models and LDA. Learn about these models for tasks like part of speech tagging and topic modeling. Okay, deep learning for NLP. Apply your deep learning knowledge for two NLP tasks for generating word embeddings, and you can also use it in RNNs, long short term memory. And gated. I need to look into these different architectures because I already know about RNNs. I've read about, like I've heard about LSTM. I never looked too deep into it. I've also heard about GRU. Never looked too deep into it. Understand these models for handling sequential data, and then transformers. Study the transformer architecture which is widely used in modern NLP tasks, including BERT, GPT, and so on. So, and then practical projects. All right. Um, in terms of NLP techniques, do I need to learn how to do a bunch of the tasks like pre-processing, stemming, etc. from scratch? Or because I'm sure there are libraries and models that would help me accomplish that. In the context of NLP, hold on. I kind of already know the answer. I'm still just asking the question to get some extra information. In the context of NLP, while it's beneficial to understand the underlying techniques and algorithms, you do not necessarily need to implement everything from scratch, especially when there are robust and well-maintained libraries available. Here's how you can leverage these libraries to simplify your NLP tasks. Okay, using NLP libraries for pre-processing. Libraries like NLTK, Spacey, and NLP pre-processing provide extensive tools for text pre-processing, including tokenization, stemming, lemmatization, and more. NLTK offers functions for tokenization, stemming, lemmatization, parsing, and I think that was part of speech tagging. It is a comprehensive library that covers most basic NLP tasks. Okay, we can go back here and let's do this. NLP tasks and techniques. Or let me write these down. I think I should at least read over some of these things, like read a little bit about them, and then decide whether I really need to try and implement it. Well, not really implement it, but try and use a library to achieve these things, or if I should just leave the entire process to a tokenizer, because a lot of this stuff eventually comes down to a tokenizer. Not all of it, but like a lot of this stuff, it eventually, like it all comes packaged within a tokenizer quite often. Okay, stemming, lemmatization, POS. I'm not going to remember that. Let's say part of speech, tagging. What else is mentioned? There was more stuff mentioned up here. Uh, word embeddings, I think that comes later on. Oh, I should look into word to vec and glove because I've seen these mentioned in other situations as well. Like I think I've seen it mentioned in a text to speech model. So word to vec, I think this is from Facebook. I'm not sure. Word to vec and glove. Okay, what else is there? Oh, yeah, let's write these down as well. So we have RNN, LSTM, and GRU. RNN, LSTM, and GRU. I think I can just leave this list here. So I'll kind of remember that, hey, I need to do this. Because I mean, I have my own like separate notepad where I write this stuff down, but I think I can leave it here. Okay, NLP tasks and techniques. Is there anything more mentioned here? Bag of words and bag of words, TF, IDF. Uh, yeah. Let's. You know what? Let's make it like this. Part of speech tagging. Um, a bag of words. TF, IDF. N grams. Capture the context of words by considering sequences of n items. Okay. Oh, this would be interesting. Yeah, no, I think you know what? I think I want to try and use some of these, at least whichever of these are available through NLTK. I want to try I want to try using them. Then hidden Markov models and latent. I need to look into how that name is pronounced, but LDA. Okay, hidden Markov models, latent. I don't know how this is pronounced. What is A? Allocation. Right. What else is there? I don't think I need to worry too much about case normalization, removing punctuation and numbers, handling stop words. Um, Actually, okay, stop word removal. Yeah. Let's look into that. But like the other stuff, like cases and stuff like that, I don't need to look into that. That's more of like sanitizing the text. Well, kind of pre-processing and sanitizing the text. Stop word removal. Right. So if we kind of go back to the basics, which I never learned because I never learned the basics of NLP, but if we go back to the basics, we can start by looking into these, right? And then the idea is to do research on these and familiarize myself with these concepts so that when I then move on to using NLP related models, I'm not going to be, you know, as lost in terms of, hey, what is this thing doing? What is that thing doing? All right, give me a second. All right, okay, cool. We are gonna do this. I'm gonna raid. Oh yeah, I'm ending. Sorry, I should have mentioned that. So yeah, I'm gonna end the stream here. I'm gonna raid this person called Jesse. I think their name is Nomadic. I think that's what it's supposed to be. They are doing some co-working or studying, one of the two. Either way, we're gonna go hang out in their stream. Um, So yeah, that's gonna be it. I've got a bunch of stuff to look into. I need to get back to doing neural network stuff. I think I want to spend some time building a neural network today. Because there was this thing that I wanted to do where I wanted to explore how well the network, actually how in general, not just how well, but how in general the network captures the relation between the the in between what, let's say between variables. I need to think fast because there's this timer, the raid timer going. But yeah, okay, that's gonna be it for today's stream. I'm gonna carry on doing this, but I need to end the stream right now. So I'll probably stream again tomorrow. I'm not sure. Hopefully I'll stream again tomorrow. But that being said, I hope you guys have a nice day, and I'll see you all next time. Peace.